All right, next slide. So our presenter today, as I mentioned, is Dan Honey. He is our resident educator, and he has a wealth of knowledge and experience in our industry. Dan, if you want to go to the next slide.
Yeah, I'm having technical issues.
Like, I don't have your bio completely memorized.
Okay, there we go.
So he has been in the industry for quite a while. I don't want to say a long time because then that makes me feel old.
Oh, go ahead.
Yeah. He has been in the industry as long as I've been alive. So, but today we are also celebrating Dan because today is Dan's birthday. So give Dan a happy birthday. Thank you, Dan, for presenting to us on your birthday. We appreciate it. You can
Happy
see
birthday, Dan.
You can see all of his all of the places that he has been that adds to his experience, and we are so grateful that he is here. Dan, I will let you take over from here.
Well, I've had the unique opportunity to participate in a number of co-authored articles from Engineered Systems magazine. The most recent one was published in the August 2023 edition on creative and innovative building designs through creative adaptive architecture, engineering, and collaboration. That article is on an innovative approach for adopting active chill beam designs for a project here in Phoenix, Arizona at 32nd Street and Camelback. However, enough of that. Let's move on to session 6, the 100% outside air systems and the importance of ventilation. Today's agenda will cover the following items. We're going to review topics that we've visited in the past regarding EPA, CDC, and ASHRAE ventilation rate statements and why they are advocating for increasing or looking at increasing ventilation rates for creating healthier environments and to reduce the risk of infection. We're then going to look at what is a 100% outside air system. Then we're going to do a deep dive and evaluate indoor air contaminants and their impact on human health and the various studies and the science behind assessing a growing amount of momentum that demonstrates that indoor air quality does impact human health and the human condition within the built environment. We're then going to introduce you, if you haven't already become familiar with it, ASHRAE's most recently released standard 241 on the control of infectious aerosols, and bring some of the language to you regarding that standard and how it's going to influence ASHRAE standard 62.1. Then we're going to look at the ASHRAE position document on carbon dioxide, and then do an evaluation of 300% outside air systems that are conducive for creating healthier environments with a better control of ventilation to each zone within a building, while also offering the promise of heightened energy efficiency. So let's begin. Let's talk about the EPA, CDC, and the ASHRAE ventilation rate statements. Going back a couple of years to the COVID era, I drew from the EPA's website, from their ventilation and coronavirus COVID-19 section, which I think is still viewable today. That section advances this statement that the important approach to lowering the concentrations of indoor air pollutants or contaminants, including any viruses that may be in the air, is to increase ventilation, the amount of outdoor air coming indoors. And it goes on to say that ensuring proper ventilation with outside air can help reduce the concentration of airborne contaminants, including viruses. The EPA in October of last year launched their Clean Air in Buildings Challenge, as it is now moving into the domain of encouraging our industry to adopt practices that will generate better indoor air quality. And hopefully we'll be able to explain why a little further along in this presentation. But one of the solutions that the EPA advocates in its Clean Air in Buildings Challenge is to optimize fresh air. ensure that outdoor air is acceptably clean or adequately filtered as it's brought into the building. In fact, it's advocating for increasing the volume of clean outdoor air at times of higher risk. And this is something that ASHRAE Standard 241 has addressed. It also goes on to say that running HVAC systems during all occupied hours to ensure clean air enters and is distributed throughout the building is highly recommended. And it also gives some control strategies for flushing out a building during the unoccupied hours to reduce the risk of contaminant concentration buildup. The Center for Disease Control argued, if you may recall, that SARS-CoV-2 is transmitted by exposure to infectious respiratory fluids. And it goes on to state that one of the ways of transmitting the virus is as an aerosolized pathogen. So consequently, inhalation of air carrying very small droplets and aerosol particles that contain virus is a path of infection. The CDC website goes on to advocate for when indoors, ventilation mitigation strategies should be applied. In fact, they even argue eliminate HVAC air recirculation altogether. In other words, bring in as much outside air as you possibly can to reduce concentrations of pathogens and also contaminants. However, if you recall in some previous presentations, we also demonstrated that increasing HVAC system outdoor air is a challenge. In fact, ASHRAE is advocating for more energy efficient systems for the development of ASHRAE Standard 90.1 and the institution of Standard 189, as well as approaching the issue of decarbonization, and they now have their position document on building decarbonization. So ASHRAE is certainly advocating for more efficient systems. However, if you merely increase ventilation alone on a conventional HVAC system, you will add an energy penalty, and it runs contrary to ASHRAE's energy efficiency platform that it has built in more recently. So why do we suggest or advise or consider looking at 100% outside air systems for addressing IAQ and system efficiency? Well, it is an efficient, healthy HVAC system design approach, and it is proven to be 25 to 30% or more efficient than conventional medium pressure VAV systems. There is no return air path to a building. Consequently, all air supplied to the building is eventually exhausted through the exhaust airstream. Energy recovery is applied to heighten energy efficiency. There is measurable outdoor air supplied to each zone, which is otherwise somewhat mystified under conventional systems. And there are multiple approaches depending on building type and designs with a lot of innovative technologies available. So let's do a quick review of some basic points that I brought forward in previous presentations on what are 100% outside air systems. The design intent of a 100% outside air system is to handle the ventilation load, the outside air load, independently from and parallel to the primary HVAC system. It isn't bringing outside air into a common air handler box that is also served by return air, mixing it and bringing that mixed air condition to a coil. You decouple the outside air from the HVAC system. So dedicated outside air units or 100% outside air units become standalone systems that handle the outside air completely. By doing that, you can actually, using a full DOAS system, you can actually reduce the airflow rate in a building by 60 to 70% if you use decoupled hydronic solutions and possibly even certainly decoupled hydronic solutions, so we'll go into in greater detail later. How is this done? Well, you decouple the total load. The total load, if you recall, is comprised of sensible heat, the energy in the air we feel and is measured at a thermostat, and the latent heat, the energy required to keep water in a vapor state, that if removed, water condenses into a liquid. So if we decouple the sensible and latent heat, we use water or refrigerant as the heat transfer medium's local to each zone as opposed to air. And there's a reason for that, and we'll look into that shortly. Building sensible load is shifted to the water or refrigerant heat transfer mediums, and building humidity is controlled by the 100% outside air unit by drying the outside air out adequately to control humidity buildup in a space. To do this, less energy is required because it takes less pump horsepower or compressor energy in order to move the heat absorbed by refrigerant or water than it would otherwise be required for an all-air system, and the consequent fan energy that is required to support those systems. So 100% outside air systems, the design intent, we would look at this option for improving IAQ because we could control the amount of outside air local to each zone. And if an owner decides, which is relevant for later in today's presentation when we bring up the topic of standard 241, we can actually increase the outside air present in each zone depending on how much outside air we bring in through the dedicated DOASH unit. Building CO2 concentrations by doing this, building CO2 concentrations can be controlled to 1,000 parts per million or below, which is a direction that ASHRAE is moving in, as we'll discuss later. You can also have better humidity control by providing outside air at lower dew points to appropriately absorb the moisture buildup in a building throughout a day. 100% outside air units, however, are not configured like conventional air handlers, mixed air handlers. They are dual tunnel designs with a supply airstream and an exhaust airstream, and some type of heat recovery device is used to take the energy from the outside, from the exhaust air to precondition the outside air coming in so that the coil does not see 100% of the outside air load. And this is a very energy efficient solution, and it can be achieved in two ways. Either sensible heat recovery, where plate and frame heat exchangers are used, heat pipe technology. There are also sensible wheels and runaround coil loops. However, they only precondition the heat energy in the outside air, not the latent or the humidity. There's another solution that offers 70 to 80% what is called latent heat transfer effectiveness, called enthalpy wheels, and these are the premium efficient system design that you might want to apply in a DOAS configuration. So why are 100% outside air systems more efficient? Let's go back and review previous slides. It all has to do with the heat transfer medium, how we move energy from a building to outdoors in cooling or adding energy indoors during heating. In an all-air system, air is the heat transfer medium throughout the building. Air, however, is not a very dense heat transfer medium. It can only carry 0.46 BTUs per pound of air. So a lot of air is required to appropriately move the amount of air necessary to maintain set points on thermostats throughout a building. Water, however, is much more dense than air and can carry 8.98 BTUs per pound of water. So consequently, you can move the same amount of energy with a lot less water, and there's a lot less pumping horsepower required to move that same amount of energy than the horsepower required for fans in an all-air system. But I invite everybody to consider as well refrigerant. Refrigerant is an even more dense heat transfer medium and can carry 88.2 BTUs per pound of refrigerant, which invited the article I wrote in July of 22 on that evaluated 3 design concepts for 100% outside air variable refrigerant systems, and the findings were very compelling. So that basically is a brief review of what a 100% outside air system is. just generally how they're laid out and why they offer the efficiency to a system that they do. However, let's look at the factors developing in our culture today. Let's look at the pandemic and what it has done to bring to our attention the importance of indoor air quality, and consequently also a re-examination of the contaminants that we live with day in and day out in our indoor air environment. And we're going to look at those conditions and how they impact human health. But first of all, I thought we could all use that, especially in the world today. I've got some good news. Doing the research for this presentation and looking at outdoor air pollution, there is good news. I was very pleased to see this. The Environmental Protection Agency published a report on the environment saying that according to the National Emissions Inventory data, they estimated that annual emissions of 187 air toxins combined decreased by 58%. From 72 million tons per year in the baseline period 1990 to 93 to 3 million tons per year in 2014. That is excellent news. Examples of air toxics include benzene, perchloroethylene, methylene chloride, solvents used within industry. And most air toxics originate from anthropogenic sources, including mobile sources such as cars, trucks, construction equipment, etc., and also stationary sources. So to see this reduction is very good news. The report also goes to say that according to Exhibit 3, emissions trends for 7 pollutants believed to be among the pollutants that contribute to the greatest cancer and non-cancer risks are attributed to air toxics according to the EPA assessment. However, estimated emissions decreased from baseline period 1990 to 93 and 2014 for 5 of the 7 air toxics: acrolein, benzene, 1,3-butadiene, etc. However, there was an uptick in acetaldehyde as well as in formaldehyde due to the prevalence of wildfires and prescribed burns. So there is an uptick in some of the chemicals, but the overall trend for outdoor air pollution is moving downward. The EPA also published this information that carbon monoxide is down 81%, lead down 88%, nitrogen dioxide 60%, etc., etc. So, and it goes on to say that despite increases in air concentrations of pollutants associated with fires, carbon monoxide and particle pollution, national average air quality concentrations remain below the current national standard. So downward pollution trends. What happened? How did this come about? Well, it actually began to occur due to an incident that occurred in Donora, Pennsylvania on October 26, 1948, when a thick cloud of smog composed of carbon monoxide, sulfur dioxide, and metal dust produced by the town's zinc plant and steel mill descended on the town, killing over 20 people and causing 14,000 people to fall sick. The response from government to this event was a recognition that something needed to be done to control air pollution, and the Air Pollution Control Act of 1955 was created. Consequent legislation on that act were in 1963 and in 1967, where amendments were added to the act until the signing into law of the Clean Air Act of 1970. And this is also really pretty encouraging. The Clean Air Act was passed by a bipartisan legislation that became law. It was unanimously passed by the U.S. Senate and passed 370 to 1 in the House of Representatives as a significant amendment to earlier laws, and it was signed into law by President Richard Nixon. And this is what's interesting, and I wonder if in the future government might lean on this statement that is embedded in the law. It says that Congress recognized a right to healthy air quality. So it's already in the language of our Outdoor Air Pollution Act. I'm wondering if that awareness will begin to influence in the Indoor Air Quality Act. Anyway, just a little bit of history. It was in 1970 on December 2nd that Richard Nixon tasked the EPA with overseeing the Clean Air Act. And the Clean Air Act includes what is called the National Ambient Air Quality Standards. And those standards include contaminant limits for a group of compounds listed in the diagram to the far right. Just a few of them are lead, ozone, sulfur dioxide, nitrogen dioxide, carbon monoxide, and a very important one that we're going to focus on today of particulate matter. So has the Clean Air Act been successful? Well, since 1990, I found these statistics. Fine particulate matter, or PM pollution, the deadliest form of air pollution, has declined 41%. Ozone has declined 22%. And the Natural Resource Defense Council report found that annual benefits of the Clean Air Act programs will prevent 370,000 premature deaths in 2020 and up to 457 deaths by 2030. So that's a pretty interesting statistic. And it also stated that in 2018, a documented 30% death reduction since 2005. So that is the good news of what can happen through good law and good legislation. So that begs the question, what about indoor environment air quality? I've heard in previous presentation on I've heard questions during previous presentations on 100% outside air systems, well, asking if we really want to bring outdoor air into a building. Well, let's examine what science and the statistics say. Anyway, what about indoor environment air quality? Which indoor air quality standards are written into law for healthier building environments? First of all, the EPA's website acknowledges that human exposure to air pollutants indicate the indoor levels of pollutants may be 2 to 5 times and occasionally more than 100 times higher than outdoor levels. The Environmental Research and Public Health Group borrowed from the World Health Organization statement that they believe that up to 3.8 people have die annually around the world from indoor air pollution. Harmful pollutants inside buildings include carbon monoxide, volatile organic compounds, otherwise known as VOCs, that you've probably all heard of, particulate matter, aerosols, biological pollutants, and many others. So, looking at indoor air pollution regarding outdoor air pollution, we have to take into consideration that if a building is getting the outside air required as a minimum for our building code standards in standard 62.1, we are not only delivering the outdoor air pollutants into a building, we're also adding all of the indoor air pollutants into the mix as well. And because the outdoor air contaminants are being injected into a box that's enclosed, they continue to build up over time. So just something to pay attention to. So what about indoor air quality standards? Are there any indoor air quality standards? And the fact is there is. OSHA created the first legally enforceable limits to exposure to pollutants indoors in 1970. And it was based on a chemical list generated in 1968. But through the advice of a book that I'm reading that I'm going to be referring to heavily today called Healthy Buildings, they invited that I go to the OSHA website to confirm what they said in the book, that OSHA has a statement on their website, and they do, and there's a copy of it down there in the lower left-hand corner, that OSHA recognizes many of its permissible exposure limits are outdated and inadequate for ensuring protection of worker health. The book that I just spoke about, Healthy Buildings, or How Indoor Spaces Can Make You Sick or Keep You Well, has been a very resourceful book, not only for what it is advancing and arguing for, but also from the pages of resources, studies, research investigation that has gone on scientific evidence. It's just in itself its own research reservoir to evaluate. So the book itself demonstrates that the built environment in itself contributes to outdoor air pollution. How is that? Well, buildings represent the largest consumer of materials of all industries in the world. For the CO2 and pollution generated to manufacture building products is substantial. The book goes on to say that approximately 80% of global energy comes from fossil fuel combustion, as consumers of 40% of that energy. That is to say that 40% of the energy consumed in the United States is through the built environment. And the emissions resulting from that indirectly infect the concentration of pollution, both outdoor and indoors. So healthy buildings goes on to ask or state that we tend to focus much more on outdoor air quality than on indoor air quality. And I ask the question if there is an indoor air quality standard, and they say no such thing. So let's look at this very closely and look at the history behind our current indoor air quality situation. We first began to experience what has come to be known as sick building syndrome in the 1970s due to the energy crisis, when outside air requirements were reduced to 5 CFM per person. Those have now increased through standard 62.1 up to 15 CFM and 20 CFM, depending on the type of building or zone served. Sick building syndrome is a set of symptoms typically affecting workers in airtight office buildings that is believed to be caused by indoor air pollutants. Something to consider, that we sealed up our buildings in the 1970s during the energy requires to reduce the use of energy. What are we doing now in our modern buildings? We are also sealing up our buildings. It was common practice 30 and 40 years ago to have buildings leak to allow for an indirect form of ventilation. As buildings are tightening up, the actual removal of contaminant buildup in a building is becoming more and more dependent upon the amount of outside air brought into a building and how much air is actually exhausted from a building. So keep that in mind. In the 6 Mega Change chapter of Healthy Buildings, the authors brought forward the World Health Organization's redefining of the meaning of the word health. The previous definition of health, or good health, is the absence of disease. The World Health Organization has now offered a new definition that states it to be a state of complete physical, mental, and social well-being. Companies are recognizing that there is value in not just a disease avoidance strategy for their employees, but also a health promotion strategy. Not only because it's the right thing to do, but also because it's proven and demonstrated that it can also help an building owner or business owner's bottom line. And we'll explore that a little more later. The World Health Organization goes on to write in their constitution that the health of all peoples is fundamental to the attainment of peace and security and is dependent on the fullest cooperation of individuals and states, and an informed opinion and active cooperation on the part of the public are the utmost importance in the improvement of the health of people. So with that being said, where do we spend most of our time? Indoors. Consequently, it begs the question, without an indoor air quality standard, why are we ignoring the 90% of where we live our lives? By the time one is 40 years old, one will have spent approximately 36 years indoors, and by the time they're 80 years old, 72 years. The average youth who graduates from high school will have spent 15,600 hours inside a school. And well, a third of our lifetime is spent in our bedrooms. So it begs the question, really is an Indoor Air Quality Act in our future. Since the Clean Air Act is being effective in reducing the amount of air pollution, it does demonstrate that there could be standards applied, an Indoor Air Quality Act that will reduce the amount of contaminants within a building. So for anyone who might think, well, certainly on a high pollution day outdoors, it's better to not have a lot of outdoor air coming in. And you know what? That could be a relevant point, which I hope to touch on towards the end of this presentation. And knowing when to control outside air to a building dependent upon appropriate monitoring of contaminant levels outdoors versus indoors, and adjusting the outside air to maximize indoor air quality at all times, regardless of the outdoor air conditions. So that's another discussion that I hope to touch on later. But the dirty little secret that the book Healthy Buildings brings out is that because we spend 90% of our time indoors, approximately 20 hours and 3 hours outdoors, the math is very straightforward. The majority of outdoor air pollution occurs indoors. Well, if you look at the actual math to that and realize that the average adult breathing rate is about 1,000 breaths per hour at a 22.1 cubic feet a day, then the amount of outdoor air pollution breathed outdoors is 30 micrograms per day, whereas the total outdoor air pollution breathed indoors in 21.6 hours is 135 micrograms per day. Because not only are you receiving the off-gassing and contaminants and particulate matter that builds up indoors, you are now also getting the outside air, if you're getting adequate outside air concentration levels as well, pumped into your building. So the Journal of Environmental Research in Public Health, in their report on indoor air pollution and related human diseases, demonstrated or listed the type of pollutants that impact human health. They're listed there, and I want to take particular attention to particulate matter, because you can verify through air monitors what PM concentration levels are. I have one in my house that I'm doing some evaluation of, a very compelling technology we have that will actually reduce my 0.3 micron PM levels from 500,000 parts per million down to 90,000 parts per million, better than an ISO 7 clean room. So particulate matter is a very good gauge of what other contaminant concentrations might be in a space. Particulate matter is defined as carbonaceous particles in association with absorbed organic chemicals and reactive metals. And indoor PM sources include particles that migrate from indoors, as well as indoor activities such as cooking, fossil fuel combustion, smoking, machine operation, hobbies, anything that off-gasses within an environment. PM 2.5, however, is the biggest concern. The smaller the particulate matter, the greater risk of ingesting that particle deep into the lungs, where it can become absorbed into the cellular walls of the lungs, and those contaminants distributed throughout our body through our cardiovascular system. So 1 micrometer is about 0.00039 inches, so it's very small. Particles of this size really do pose the greatest risk to human health. Well, looking at global PM 2.5 contaminant levels and what type of studies have been done, well, PubMed lists over 7,000 scientific papers on PM 2.5 and its health impact. And there are some interesting statistics. Mortality rates increase by 7% for every 10 microgram per cubic meter of PM 2.5. Hospital admissions globally increase over 4% for every 10 microgram per cubic meter long-term increase in PM 2.5. 5% of lung cancer deaths globally are attributed to particulate matter, etc. So there is a human health impact by levels of PM2.5 concentrations in and of itself. In classrooms, indoor air quality also has an impact. There are over 200 scientific studies documenting how the school building influences student health, student thinking, and student performance. Cognitive testing of students show a 5% decrease in the power of attention in poorly ventilated classrooms, equal, to some researchers' opinion, to a student's missing breakfast. In a study of over 4,000 sixth graders, lower ventilation rates were all independently associated with a higher incidence of respiratory symptoms, and inadequate ventilation was also associated with more missed school days. A study of over 3,000 fifth grade students showed that they had higher math, reading, and science scores in classrooms with higher ventilation rates. And there's also a thermal comfort factor apparently as well. In a study in New York City of exam records for nearly 1 million school students, it was found out that on a 90-degree day versus a 75-degree day, that there was a 14% greater failure rate on exams. The National Lung Association, in their From Absences to ACEs under reduced absenteeism, states poor indoor air quality can lead to higher rates of respiratory infections, allergic responses, and adverse reactions to chemicals. Asthma is one of the leading causes of school absenteeism, causing an estimated 13.8 million lost school days in children from 5 to 17. And if any of you parents out there have had children with asthma, as my wife and I have had, we know what a concern that can be. The National Institute of Environmental Health Sciences on indoor air quality advances how indoor air quality can affect adults. Poor indoor air quality can affect the cardiovascular system. A study partially supported by the NIEHS found that markers of cardiovascular disease risk appear when ozone levels are even lower than current EPA air quality standards. Exposure to short-term indoor and outdoor ozone was linked to increased blood platelets, a risk factor for clotting and increased blood pressure. The cognitive effects occur, our ability to focus and concentrate. Air pollutants, including PM, allergens, oxides of nitrogen, etc., have been associated with impaired health and performance in children and adults. And it goes on to say that air quality within an office affect employees' recognition function, including response times and ability to focus. And it may also affect their productivity. Another finding regarding cancer is that long-term exposure to radon and other indoor air substances to increase lung cancer resulting from secondhand smoke, asbestos, arsenic, and other forms of silica and chromium. And it goes on to say that even indoor air contaminants such as formaldehyde exceed acceptable levels in some childhood learning centers. Another issue that impacts indoor air quality is carbon dioxide. ASHRAE Standard 62, 1999 replaced the original carbon dioxide limits in a building from approximately 1,000 parts per million to 700 parts per million above the ambient outdoor levels, which at the time it was written were about 350 to 375. However, our outdoor CO2 levels, certainly in Phoenix, Arizona, now read on a bad day up to 550 parts per million, which means that if a system is designed to maintain the 700 part per million differential, our CO2 indoor levels are now 1,200 to 1,300 parts per million. And the article referenced here, revisiting the 1,000 parts per million CO2 limit by Mr. Strum, in an article posted in the ASHRAE journal, said that CO2 at levels as low as 1,000 parts per million induce significant reductions, can induce significant reductions in cognition and decision-making abilities. Wouldn't be surprising to see that ASHRAE targets perhaps 600 to 800 parts per million, but first I think they're going to probably settle on 1,000 parts per million. So how does CO2 impact performance in human health in the indoor environment? Well, first of all, the source of most CO2 in a building is human respiration. And in one study, it was found out that at 100 non-problem buildings in the US, 95% of the buildings read 1,500 parts per million. The Lawrence Berkeley National Laboratory did a study of 162 classrooms, finding an average 1,500 parts per million CO2 concentration. And in Texas, 1 in 5 schools tested peaked out at 3,000 parts per million. You ever ask yourself your question, maybe, why do you feel all of a sudden so tired walking into a conference room or walking into a university classroom where there are a lot of occupants, and you just start feeling tired? Well, it could be due to the CO2 levels. So the actual study goes on to say, or Healthy Buildings goes on to say that one solution to controlling CO2 levels in a building is to increase ventilation, because the outdoor CO2 levels are significantly below indoor levels. So looking at ventilation, volatile organic compounds, and CO2, we can help to reduce the CO2 levels in the space by doubling prescribed CFM levels from 20 CFM per person to 40 CFM per person. So pretty interesting. So this is one aspect of the equation, but I mentioned early in the presentation that bringing an environment of better indoor air quality could actually help a business owner's pocketbook by having a healthier environment. The book Healthy Buildings has a chapter that evaluates how higher ventilation rates can impact the income of a business. And it does so by looking at the ventilation rates and making a comparison between a conceptual design of 20 CFM per occupant versus 40 CFM per occupant. It uses a sample business consisting of 40 employees, average salary about $75,000 a year, which breaks down into the following numbers. A business's overhead is comprised of about $3 million in payroll, $300,000 in rent, and $30,000 in energy costs. Well, if you double the CFM of outdoor air or ventilation air to the building from 20 to 40 CFM, it's really rather interesting. And there are a lot of studies that we just didn't have time to go into in this presentation that show that improvements in thinking, like focused activity, information usage, and strategy, results in more billable hours, more client assignments, and more engagement sold, resulting in just a 2% boost in productivity of a 9% bottom line increase of revenue for that firm. And by the way, the 2% is the lowest of a 2 to 10% range argued for in the Healthy Buildings book. So not only is indoor air quality a good idea because it's the right thing to do to protect occupants of buildings, but also if owners take advantage of it, they could actually be enhancing their bottom line because their workers are more alert, ready to focus, and are able to comfortably think through the problems they're challenged with every day to come up with more productive solutions. So looking back and just all of the information covered here, we can say that there are numerous studies and research has been done that more than suggest one way to improve indoor air quality and occupant health is to increase the ventilation rate. Data is available to demonstrate improving IAQ is one good way to boost employee productivity and to increase a company's bottom line, which begs the question as well, will insurance companies begin lobbying Congress to address building IAQ? If IAQ is impacting health to the ways that science and the industry is demonstrating, then it wouldn't surprise me that the insurance companies realize that there's a lot of money to be saved by creating healthier environments and reducing the medical impact of poor indoor air quality. So remember, consuming more energy, however, to provide more ventilation does not require more system energy usage if you apply a strategy known as 100% outside air systems. Before we begin to approach that topic, though, let's quickly review Standard 241 on Control of Infectious Aerosols. This standard was just released in June. It was the fastest standard ever written, over 6 months. The purpose of the standard is to establish minimum requirements for control of infectious aerosols to reduce the risk of disease transmission in the occupiable space. In the foreword of the standard, it states that the catalyst of the development of Standard 241 was a discussion between ASHRAE and the White House COVID-19 response team and the need for new and better IAQ standards. And they came to the conclusion that engineering controls, dilution, ventilation, filtration, air disinfection can help reduce the risk of active pathogens and also, I would think, contaminants. The standard goes on to state that airborne transmission of communicable diseases occurs when a susceptible person inhales active pathogens. So the standard addresses only long-range airborne transmission within the built environment. That's its focus. In the scope of the standard, it states that the intention of Standard 241 is to incorporate similar provisions into existing ASHRAE IAQ standards, such as 62.1. Perhaps this becomes part of the standard. Maybe it's listed as an optional requirement. It's still open. But regardless, it's apparently intending to make its way into 62.1. In the foreword of the standard, requirements are listed. A requirement that systems comply with the requirements of the applicable ventilation and indoor air quality standards outlined and stated by 62.1 and 62.2 is certainly a given. Standard 241 then provides additional requirements for an infection risk management mode of operation, an IRMM, that applies during periods when higher levels of infection risk mitigation are desired either by building owners or are required by local authorities. So the buildings are to be designed with a resiliency to move into a mode of operation that meets the infection risk management mode guidelines. So what is infection risk management mode? It is the mode of operation in which measures to reduce infectious aerosol exposure and documented building readiness plans are active. Part of the IRRM is to deliver the appropriate amount of equivalent clean air to the breathing zone. Requirements for infection risk management are given in terms of equivalent clean airflow rates in units of CFM or airflow per occupant, otherwise known as ECAi's. The definition of the equivalent clean air rate is the theoretical flow rate of pathogen-free air that, if distributed uniformly within the breathing zone, would have the same effect on infectious aerosol concentration as the sum of actual outdoor airflow, filtered airflow, or inactivation of infectious aerosols. So it isn't just limiting bringing outside air into the space, it recognizes also properly treated return air. The language is very clear that the requirement for a space or system can be met not only by outdoor air, but also filtered recirculated air and air disinfected by various other technologies. Requirements for air distribution in mechanically ventilated and mixed mode buildings and requirements for application of in-room air cleaners are addressed in paragraph 7 under air cleaning. So the technologies that are used have to meet standards or guidelines written in the 241 standard. The minimum ECA1 airflow rate can be met either by outdoor air meeting the minimum ECA requirement per person, or any combination of outside air providing minimum outside air per standard 62.1 is met, and supplemental return air treated by filtration or other air disinfecting technology. So how do you calculate the ECA value for a building or for a zone? It is basically the assigned CFM per person ECAi value times the number of occupants in that space. So if you look at a conventional building for a conventional office where we would see 20 CFM per person, that would now be bumped to 30 CFM per person. And there are some values in for commercial and retail I'm showing here that the minimum ECA ventilation rate would be 60 CFM per person in food and beverage facilities, 80 CFM per person in a gym, auditoriums 50 CFM. Well, you can see this is going to be a challenge for a lot of our conventional HVAC equipment design for these systems to ramp up into IRMM mode to meet the ECAi requirements. Section 7 of Standard 241 lists the type of air cleaning technologies and filtration methodologies that are available in the industry to reduce pathogens and contaminants, and each of those installations are outlined specifically in the standard for manufacturers to reference to make sure that they test their products in a way that will allow them to comply with the standard to generate the appropriate ECAi value. Now, another topic that I want to talk on here, and I'm going to be very quick with this, I just advocate that you read ASHRAE's position document on indoor carbon dioxide because I want to be sensitive to time here. There's a lot of material being covered. So let's just quickly run through the position document on indoor carbon dioxide. The position document states that it is really discusses the role of indoor CO2 in the context of building ventilation. It goes on to state that the use of CO2 as a metric of IAQ in ventilation, the impacts of CO2 on building occupants, the measurement of CO2 concentrations, the use of CO2, etc., are all expressed within the position document. The abstract also goes on to say that this document recommends research into the impacts of CO2 on occupant health, comfort, and performance, and on the application of indoor CO2 concentrations in building operation. It goes on to say that CO2 concentrations do not provide an overall indication of IAQ, but they can be a useful tool in IAQ assessments if uses understand the limitations in these applications. So ASHRAE takes a little more measured approach to CO2 concentrations in evaluating indoor air quality for reasons that are clearly outlined and stated within the position document. It does go on to say that differences between indoor and outdoor air CO2 concentrations can be used to evaluate ventilation rates and air distribution using established tracer gas measurement methods, but accurate results would have to be evaluated per each application. It does go on to say that health and performance impacts in indoor CO2 and concentration ranges typical of non-industrial indoor environments need to be evaluated. Physiological impacts of elevated CO2 concentrations, such as changes in blood chemistry and respiration, also need to be further evaluated. And it goes on to say that recommended research needs to be done regarding concentration measurement and including sensor performance and sensor locations, where they make the most sense within buildings, and also on CO2 concentration in relation to ventilation rates and occupancy needs further studying as well. But it does go on to say, and it demonstrates what I mentioned earlier, that indoor concentrations of CO2 greater than 1,000 parts per million have been associated with increases in self-reported, non-specific, commonly referred to as sick building syndrome symptoms. So it does recognize that, and it's looking at 1,000 parts per million as perhaps the minimum baseline for CO2 in future standards. So quickly, as we just about we have run out of time, Let's do a quick review about what type of 100% outside air systems will allow building owners and design teams the greatest flexibility to condition a building with the appropriate level of outside necessary to enhance and support good indoor air quality. In the past, we've discussed 100% outside air active chill beam systems. We demonstrated that ventilation air supplied directly to each zone by these systems. These are 100% outside air systems, and these systems offer easily 30% to 35% greater energy efficiency than conventional medium pressure VAV systems. How do they do that? Well, they decouple the sensible load from the latent load and drive as much sensible load to the water side, which is far more dense, and it requires a lot less pumping horsepower to move the same amount of energy otherwise required in an all-air system. These systems are, decouple the total load. Chilled water and hot water is piped directly to each zone, where the sensible load in each zone is delivered to the chill water or hot water loop, so you have local conditioning. Latent load in these systems are by the 100% outside air unit, by adequately drying out the outside air to absorb the humidity infiltration and buildup in a building to maintain relative humidity set points within a building. Design airflow is 50 to 70% less than compared to a mixed air system, so consequently, your energy savings is in fan horsepower. The design of dedicated outside air systems are important for maximizing the effectiveness of these units, and Veritech can absolutely support you in these unit selections and design characteristics. Another 100% outside air system that I think is very compelling are passive radiant cooling and heating systems, because unlike conventional systems, they use all four modes of heat transfer: conduction, evaporation, radiation, and convection. Radiation and convection do not require energy to bring about the heat transfer effect. These systems use the electromagnetic spectrum to absorb or disperse sensible heat energy within a building to control the environment, and they use displacement ventilation to create a thermally stratified environment that allows for convection to go from lower areas in the room to allow for room air, cool conditioned room air supplied at lower levels of the room to migrate upwards along heat sources in the space where warm contaminated air is exhausted from a building. And since these are 100% outside air systems, none of that warm contaminated air is redelivered back into a building. So we can certainly support you in system design concepts with passive radiant cooling and heating systems, and provide further information on them as they may be required. I do want you to consider, though, if you really want to optimize the system, because low in space air delivery systems are being evaluated very closely by ASHRAE, and thermally stratifying environments are demonstrating to be very effective ways to enhance indoor air quality and to reduce the risk of infection within a space. But stay tuned for that in the upcoming two further discussions on thermally stratified air systems and underfloor air systems. Another one to look at is 100% outside air variable refrigerant systems. These two can be 100% outside air systems where the DOAS unit is parallel for the VRV system. And these systems can offer 19 to 26% better energy efficiency than untempered outside air variable refrigerant solutions, with many other advantages as well. The presentation lists adequately and will be accessible to you on our website. So also, if you wanted further support in evaluating 100% outside air systems, I invite you to consider going to Engineering Systems Magazine, where I have had, within the last year, well, a year and a half, 3 articles that give 3 different solutions and for adaptive 100% outside air system approaches. That is it for today's presentation, and I'm sorry to go 5 minutes over. Full apologies. Are there any questions?
There are no questions in the chat, but if anybody has any, feel free to unmute yourself or pop them in the chat. All right, we don't want to take up too much more of your time. So if you do have any questions, you can always feel free to follow up with myself or with Dan or with your salesperson here at Veritech, and we'll make sure that we get your question answered. Dan, thank you so much.
Kelly, thank you. Thank
And-
all of you for joining us today.
And happy birthday. Everybody's saying happy birthday in the chat. So,
I
oh,
think I'm going to go out and enjoy the rest of the afternoon.
Absolutely. One question did come in, so I'll just send it to you, Paul. I'll send it to him in an email. So Dan,
I'd be happy to. I've done a lot of research on this. Be happy to answer any questions that I can, and I'm sorry to rush through so much information.
No worries. Otherwise, I will stop recording. We'll end this. If anybody wants to jump off, Paul, if you wanted to stay on and ask your question, we can do that as well.
Absolutely.
Thank you, everybody, for attending.
Thank you.